So one thing that I've been involved in over recent years is quantum computing. And I always recommend this book to people because I really like the author, although technically speaking, there are many much better quantum computing books out there. And so I wanted to use this particular angle to actually talk about post-quantum cryptography. So instead of just jumping straight to the algorithms and just poking around in the code, I would like to spend like the first half of the session actually talking about how quantum computers can attack our existing cryptography, why they can do this, and sort of walk you through a little bit how these things can happen. So hopefully this will give this session a little bit of a unique flavor compared to maybe some other stuff that you might see around this particular field. And then towards the end, we will look at some code. It will be .NET code because I have to show some code, but all of the theory is universally applicable. And this is the company that I work for. I'm actually based in Switzerland, so if you've never been to Switzerland, then you should come and visit. It's quite a nice place, and the flag is a big plus as well. So I don't know. These things just come out of me. I don't know. So let's start with a little warm-up, but we only have professionals here, so we'll not spend too much time in this part of the session. It is just to establish the baseline and make sure that everybody's on the same page, right? When you think about cryptography, I think the first thing that comes to mind is symmetric cryptography. Even when you talk even if you teach cryptography to kids, right? Like you start to show them the basics, they immediately think about the setup where two parties share the same key and they use it for some secret communication. And of course, in such a setup, like symmetric encryption, a key plus a message gives you a ciphertext, and then a key plus a ciphertext allows you to recover the message. Now, we would like to use this everywhere, and it is extremely popular, right? So the most popular symmetric encryption algorithm is, of course, AES, Advanced Encryption Standard, and even all the strange, dangerous three-letter agencies in the US, they would use AES for top secret classified information. And symmetric cryptography is something that is fast, reliable, well understood, and it's something that we want to deploy everywhere. But if you would like to use symmetric encryption and symmetric cryptography for communication scenarios, then you quickly run into this chicken and egg situation. Now, in general, deploying cryptography for communication scenarios simply means that you are converting an insecure communication channel into a secure communication channel. Now, with symmetric cryptography, in order to do this, you have to distribute the key somehow. And in order to distribute the key, you need to have a secure communication channel in the first place, which is this chicken and egg problem. And the way this is solved with asymmetric cryptography is, of course, by having a pair of keys. And the public key is normally derived from a private key, and that is done using some sort of a trapdoor function. So a function that is relatively easy, relatively cheap to execute, and it gives you the public key relatively easily, but it's prohibitively expensive to go the opposite way. And it is not something that is impossible, it's just computationally prohibitively expensive. Now, with such a setup, of course, now you can publish the public key, and anybody can use this public key to create a ciphertext, but only the person in the possession of the private key will be able to recover the original message. And we use asymmetric cryptography for two main use cases. So the first one is for the key exchange or establishment. So basically to address the chicken and egg problem that we mentioned. So in protocols like TLS, the initial handshake would be done using asymmetric cryptography. And as soon as that shared secret is established, we can switch over to symmetric cryptography because it's easier and faster. And the second use case are digital signatures. So basically ability to create and verify signatures and being able to deal with things like content authenticity and integrity and verify that. Now we are going to be covering both of those as we go forward, but these are the two major use cases. And today's cryptography, asymmetric cryptography that is deployed out there, so there are many variants and schemes, but pretty much 100% of what we are using falls into these two categories, right? Either RSA or elliptic curve cryptography. And they are based on different mathematical problems that underpin this relationship between the private and the public key. So in RSA, that is factorization of large composite numbers, and in elliptic curve cryptography, that's the so-called discrete logarithm problem over elliptic curves. Now, in this session, we are going to be looking at RSA because it is mathematically simpler, so it's easier to reason about. But all the theoretical discussion that we'll be having is actually equally applicable to both of those. And as we will see, even though these mathematical problems are actually different, under the hood, once you sort of strip them down, they are actually quite similar to each other. All right, so the plan for the next 5 minutes is to basically go through material that you would learn in 1 year university course. So I wanted to just introduce the basics of quantum computation. And the basic unit of information, the basic unit of information in quantum information theory is a qubit, a quantum bit. And in classical information theory, the basic unit of information is a bit, a 0 or a 1. Now, a qubit and a bit actually have a lot in common because a bit can only be a 0 or a 1. A qubit can only be ever seen in one of two possible states, the so-called observable state or basis state. And we typically denote them with this symbol here. This is called a ket in quantum mechanics. It's actually mathematically a vector, but it's inconsequential for us today. And basically, so this would be ket 0, ket 1. And because there are only two of them, we can easily map them to 0 and 1. And so basically, if we stop here, we have reconstructed a regular computer, or as we call it, classical computer, inside a quantum computer, right? But as it turns out, when we are not observing a qubit or a quantum object, it can actually undergo this quantum effect. So it can experience effects that are only available in the quantum realm. And one of those is, of course, superposition. And that is something that we all know of because of the famous case of the cat of Erwin Schrödinger that was both dead and alive at the same time. And of course, in that case, the two observable states were being dead and being alive. And as it turns out that when you are not observing a qubit, so basically when the program executes in a quantum computer, the qubit can enter a mixed state of being both ket 0 and ket 1. So basically, mathematically, it's just it's basically a superposition of the two vectors, right? That's why we call it a superposition. And this is something that we don't experience in our everyday reality, and that's, of course, what this Schrödinger cat paradox was all about. But it's something that is fundamental to the quantum reality, right? You can experience this in a lab, for example, in a device called interferometer, where you have a photon that can be traveling along one path in the interferometer or another path in the interferometer. So these are things that spatially are separate from each other, right? But when the photon is in a superposition state, then it means it's in one arm of the interferometer or in the other arm of the interferometer, superposed over each other. So it's technically in two places at once. And it gets really bizarre really quickly. But the point is that this impacts very much how we can think of program evolution in a quantum computer. Now, in the most abstract way, if you think about what a computer program is, then you can think of it as in a sort of a functional way, right? In a classical computer, you simply have some input, which is expressed in bits. Then the program executes, so you have some sort of a state space of the program where the calculations or computations are happening. And then you have the output of the program, which is also bits, right? So at any point, you can stop, attach a debugger, and see what bits are where. Now, in a quantum computer, it's sort of similar in the input phase and in the output phase. But the execution is much different. So in the input phase, it would be similar because at the end of the day, our information is binary. So if I want to put something into a quantum computer, well, I take the binary information, I map this to state ket 0 and ket 1, and let quantum computer calculate from there. Now, the output phase is also similar because we already said that you can only ever see a qubit to be in a state ket 0 or ket 1. So effectively, these are mappable one-to-one to a bit, so it's like getting bits out of it. But during the execution of the program, the qubits can undergo those quantum effects and, for example, can be in a superposition state. And basically, this is the strength of quantum computers, right? They are able to take algorithmic advantage of these quantum effects, like superposition, but also others, like quantum entanglement, quantum interference, and so on. And in this particular case, we call this quantum parallelism. Now, this is a very subtle effect, so we should not read too much into this. But the way you can begin thinking about this is if you consider a function f of x, right? So, in a classical computer, if you have a function f of x, you simply pass different values of x to this function and see what's the result. Now, in a quantum computer, you could theoretically create a superposition of all the possible values of x. So you now have a superposition of all the possible values that you might be ever passing to this function, and you can actually try to calculate from there. Now, here's a visualization that tries to capture this. It's very difficult to visualize, but this is one of the best that I have found. This is actually coming from a paper that was published by KTH Royal Institute of Technology. That's actually in Stockholm, so I apologize for that. But it's a good visualization. So what happens here is that we start with some sort of an input to this program, and in this case that would be like 5 qubits. And then what happens is that every single qubit will go through this H transformation, this H gate. And the H transformation is a fundamental instruction in quantum computing, and it basically places a qubit in a superposition. So if a qubit can be a 0 or a 1, or ket 0, ket 1, then after going through an H gate, it is now in a superposition state of effectively being a sort of mixed state of ket 0 and ket 1 simultaneously. And since we do this for all the 5 qubits that are being input here, then basically, if you have 5 qubits, then you can never see them in state 5 zeros, or 5 ket zeros, or 5 ket 1s, right? Or anything in between. So that's 2 to the power 5 possibilities. But since you have created now a superposition of all the possible values, you literally have all the 32 outcomes of this program that are now represented by these lines here. So now the state space within this program now has sort of access to all the possible outcomes of this program, right? We will never be able to see them, because what we will get out of a quantum computer, right? We will get, in this case, 5 qubits that are either ket zeros or ket 1s. So it will be really one of those 32 outcomes. But during the execution, all these possible outcomes are actually there in the state space of the program. And this is really difficult to comprehend, because if you consider having 256 qubits, for example, which is actually not that many, then the state space of this program is 2 to the power 256, which is about 10 to the power 80, which is actually a number that is larger than the amount of atoms in the entire universe, right? But it's actually there. And now, so the trick of writing a quantum algorithm is to steer the evolution of this program in such a way that some of these lines basically get amplified and some of them disappear. So at the end, we have to arrive at just one, right? So it's almost like you are filtering through results, and you are trying to find out the one that you are interested in and amplify that, and let the other one sort of get cancelled out, so that when you arrive at the final result, it is the one that you are looking for. It is a fundamentally different approach to computation, because in a classical computer, you can sort of think of computation as working on this blank canvas, or having a clean slate, where basically you execute a function and the result comes out and is there. And here it's almost like the opposite. All the outcomes are out there in this program state space, and you are trying to steer the evolution of a program in such a way that you end up with just the one that you were interested in all along, right? Now, we are going to come back to this in a moment, but we'll take a brief detour into RSA. So one of the most widely used public-private crypto systems out there is RSA, and it's based on factoring problem. It dates back to, I think, 1974, so it's over 50 years old. Now, this is how RSA works. It is surprisingly simple for how powerful and how useful it is. So you start by picking 2 huge prime numbers, P and Q. You then pick a public exponent E, which is almost always 65,537, so it is effectively a constant. Then you multiply P by Q, which gives you an N, and you publish this N, and that is your public key. Now, if somebody would like to encrypt something for you, they take their message, they have to convert it into a binary format, so effectively give it a numerical representation. They raise it to the power E, calculate modulus with N, and that is the ciphertext. Now, in order to decrypt, you have a different formula, which is a bit more complicated, but you can see that P and Q are there, right? So in other words, the P and Q are a de facto private key, right? And if we strip down everything, basically the security of the whole thing is this. You know N, but you will not be able to find out the values of P and Q, even though N is just P multiplied by Q. And it sounds trivial, but actually, as it turns out, given the sizes of the numbers involved, it is a tremendously difficult problem. So we think that the largest supercomputers would take probably hundreds of millions of computational years to actually be able to chip away and attack RSA. So that's why we use it. Now, this is a JSON Web Keys document, and I'm sure everybody has seen this at some point. So if you are doing any OIDC or OAuth 2 integration, you will be consuming a JSON Web Keys document to be able to learn what are the public keys that the tokens have been signed with. And in this case, this is coming from Google. So if you are doing integration with Google, with sign-in with Google, this is what you will be consuming. And you can see that they are publishing 2 keys in this case. Both are RSA keys. And this is the N, and this is the N. And this is E. This is actually 65,537 in base 64. And of course, the P and Q is not being published because that's private. So now if I had the technology to actually take the N and recover the P and Q out of it, I will be able to self-sign Google tokens, right? So I would be able to impersonate any Google user with this, which is extremely powerful. And of course, this would be a devastating attack that I could do on Google. But of course, if I had the technology to do that, to take the N and recover the P and Q out of it, then I probably have more interesting things to attack than Google, right? I'd probably go to my bank first, or maybe not to my bank, maybe to your bank, or maybe to your sovereign wealth fund, I don't know. So in 1994, this paper came out. This is probably, I'm biased because I've been working with quantum computers, but it is one of the most important papers in the history of computer science. So in this paper, Peter Shor, he was working at IBM at that time, now he's with MIT. He introduced an integer factorization algorithm for quantum computers that actually achieves exponential speedup compared to the best classical algorithm that we have. And of course, exponential speedup is like, we know this from the corona pandemic. Exponential is massive speedup, right? Amazing thing about this algorithm was that it was a theoretical algorithm for a theoretical device. At that time, there were no quantum computers. So we had this model of how we could work with quantum computers, this theoretical computational model. This was developed at the end of the 1980s by David Deutsch primarily. But they still were sort of hypothetical devices. We never knew whether we would be able to build them. So it was a theoretical algorithm for this theoretical device. The first quantum computer actually was built 4 years later, in 1998. It was a small experimental 2-qubit machine. It was based on the technology called nuclear magnetic resonance, which actually is the same core technology that is used in MRI scanners. So the next time that you see an MRI scanner, then you can think of it as a sort of a cousin of a quantum computer. How would you go about attacking RSA with this algorithm? Well, you start by picking an A that is smaller than N. It has to be relatively prime to it. And then you consider a function like this. F of x is equal to a to the power x modulus n. And you start at 0, and you do this for integer values of x. And as you plot this function for a long time, probably, you should realize that the function starts to repeat itself. And that repetition interval is what we call the order of the function or the period of the function. And once you have that, then you are almost there, because if it's even, then you can calculate the candidates for P and Q, and this is done using the greatest common divisor algorithm. This is something very simple because, we've known this since the times of ancient Greece. If it's not even, then you go back to step 1. And so in reality, you have to repeat it many, many times. And that second step is what is prohibitively expensive, because 1 and 3 you can do on a classical computer easily, but it's 2 that is actually super, super slow. So here's an example of attacking 4-bit RSA, right? So we imagine that Google published n equal to 15. What we are going to do is we are going to set a to 13 because it's smaller than 15, is relatively prime to it. And then we will plot the function 13 to the power x modulus 15. And you can see this function is already plotted here. And it's obvious that the repetition interval is 4, right? So we have found the period of the function. So we just stick this 4 into the candidate formulas, and this gives us greatest common divisor between 170 and 15, and 168 and 15, and that's 5 and 3. And basically that's that, right? So we have recovered the P and Q out of the N in this case. And so if you have a 4-bit RSA security somewhere, then you have to quickly update because there's now a 0 day. we have successfully cracked it. So what Shor realized is that basically the second step, so this order finding of the function, that is basically a problem from signal processing, right? Because that's effectively what you are processing. You have a signal and you are trying to find out sort of the pattern in it. And in signal processing, we would use techniques like Fourier transform, like fast Fourier transform, digital Fourier transform. And then he realized, you know what, on a quantum computer, I could use a quantum Fourier transform. And basically, this is where the exponential speedup comes from. So this diagram here is what we call a circuit diagram for Shor's algorithm. This is how quantum algorithms are typically represented. Basically, each horizontal line represents here a qubit. And in this case, we have, actually, I have this little tool. I should use it. So you can see that we start with all the qubits in state ket 0. And of course, we have these dots here. So this means that there are many of them. And then notice that the first operation that each qubit will go through is this H transformation. So basically, like prerequisite to do anything is that everything goes into the superposition state. So basically, at this point, all these qubits are in a superposition of all the possible values that they can ever have, which is, I think, quite cool. And then ultimately, there is here the quantum Fourier transform. It's actually an inverse quantum Fourier transform, but doesn't matter that much. But fundamentally, if you look at this and you compare it to the earlier visualization that we used, it's actually surprisingly similar because that is effectively the essence of many of these quantum algorithms. So at this point, you might protest. You might say, OK, but this is RSA, so we don't care about it so much. We anyway use elliptic curve cryptography almost everywhere. And that is true, especially in TLS. Like in TLS 1.3, RSA is even forbidden for key establishment. But the original Shor's algorithm, and this was actually already in the paper. I mean, we didn't mention this. If I go back here, you can see here even the title, right? It's an algorithm for prime factorization and discrete logarithms. So it can actually be used to attack elliptic curve cryptography as well. It's just mathematically easier to reason about RSA because it's a bit simpler. Plus, there is a lot of research like this paper here from our friends at Microsoft that actually shows that it's even easier to attack elliptic curve cryptography on a quantum computer than it is to attack RSA in terms of the resources needed. But the reason why we want to use elliptic curve cryptography anyway is because it just gives us sort of a setup where it's much easier to keep changing the keys, right? In RSA, the established keys are these long-lived keys. So in general, it is then more troubling for the attacker to have to decrypt many keys rather than just one. So that is the primary reason for this. So you might ask at this point maybe, so what is then the size of a quantum computer that's actually needed to be able to execute such an attack? And this is something that has been changing over years. And up until like last month, the best estimation that we had was this paper here from Craig Gidney at Google Quantum AI. It was actually called Google Quantum, but now everything has to be AI, so it's now called Google Quantum AI. It's from June last year. And basically in this paper, he estimates that in order to attack RSA 2048, we need about 1,400 logical qubits, so basically algorithmic qubits to actually execute the algorithm. But this is not physically attainable, right? Because quantum computers, they make a lot of errors because they are very susceptible to environmental noise. And so what normally has to happen is that you have to apply this error correction code. And then in this paper, he assumed this so-called 2D surface code architecture, which is a sort of a standard way of doing error correction with a 0.1 error rate. And that, you know, effectively increases this 1,400 into almost like 1,000,000 qubits, which is anyway a massive progression because he did this estimation 5 years back, and at that time it was 20 million. But this has actually changed dramatically last month. About like 3 weeks ago, this paper came out. And this is from a startup in Australia, Iceberg Quantum. And they basically took the same foundations, algorithmic foundations that Craig Gidney did in his paper, the same logical requirements, but swapped the 2D surface code architecture with a like more advanced, the so-called low-dense parity check architecture. And then on top of this, they also have this sort of pinnacle architecture that they call it, which is like a slightly different way of how things are interacting with each other. And long story short, this allowed them to actually improve this by like a factor of 10. So suddenly we are down to like about 100,000 physical qubits, which basically accelerates the whole timeline for migration to post-quantum cryptography by probably at least 2 years. Now, so this is a big deal. So this really just happened, like I think in mid-February. So where are we with today's hardware? Now, it's a difficult question to answer because there is no universal quantum hardware, right? So there are different ways, we call them hardware modalities, for building a quantum computer. So there are quantum computers that are based on trapped ions. There are quantum computers that are based on superconductors with Josephson junctions, the so-called superconducting qubits. There are quantum computers that are based on light, photonic quantum computers, and so on and so forth. Plus, the count of qubits is just one aspect, right? But the other is the error levels, the so-called coherence time, the fidelity, the connectivity between qubits, and so on. But for the sake of not stalling any further, basically this is where we are today. So at best, we can say we are up to like 100 logical qubits and up to like low thousands of physical qubits. Again, this is just because things are very difficult to compare. So it seems like we are still far away. But then the problem is, and this is a very nice quote from Craig Gidney, it actually is in response to this Pinnacle paper that just came out, where he says that, okay, there will be these things, like this Pinnacle paper, that basically accelerates the timeline by 2 years maybe. And so if you are planning to look into this thing only when it becomes a real pressing threat, then it might be too late. Plus, on top of this, there are timelines like this one. So this is one of the companies that's building quantum hardware. It's called IonQ. And they are extremely bullish in terms of what they are promising. So this is where we are today, right, 2026. And they say 256 physical qubits, 12 logical qubits. Doesn't seem like much, but also extremely low error rates. And because of those extremely low error rates, they actually need fewer physical qubits to produce logical qubits. And then on top of this, they say, you know what, we've done all the foundational work. We now have a very clear path to scale. And they say, 2028, we will have 1,600 logical qubits. 29, 8,000 logical qubits. 2030, 80,000 logical qubits. So these are numbers far exceeding what is needed to actually decrypt RSA or elliptic curve cryptography. And this is like 2, 3, 4 years away. So we will see whether they deliver on this, but it's just something to keep in mind. And then, of course, there is this typical threat, which is called harvest now, decrypt later. So, of course, if you have a threat actor, they can just collect data now and just decrypt it when they have the technology. All right, so we talked about asymmetric cryptography. What about symmetric cryptography? Is this vulnerable to quantum computing attacks? And the answer is yes, but we are not worried about this. And the reason why yes is because of this paper. This is 1996. And it's a sort of innocent paper, or with an innocent title, a quantum mechanical algorithm for database search. But actually, this is a search algorithm through an unsorted data set, which basically means you have a function f of x that gives you a y, you know this y, and you need to find out the original x. And this gives you a quadratic speedup over the best known classical algorithm. So what is a quadratic speedup? It means that if you have 100 steps to achieve something, you can do this on a quantum computer in a square root of 100, so in 10 steps, which is super impressive. But it's only super impressive if you go from 100 to 10, because a square root of a large number is still a massive number, right? So here's an example. So we could use this algorithm to brute force AES 256. And to brute force AES 256, you need 2 to the power 256 steps. Now with this algorithm, you can do this in a square root of 2 to the power 256, which is 2 to the power 128, which is still a massive number. So we are not really worried because we can easily offset this. And this is basically the full picture, right? So with AES, basically AES 128 should no longer be used. And AES 256 should be considered to be as strong against quantum computers as AES 128 was against classical computers. And then for RSA and elliptic curve cryptography, basically nothing works anymore. All right, so this now transitions us finally to post-quantum cryptography. Now, in 2016, NIST announced this crypto competition to develop new standards. And the winners, the first winners, were announced in 2022, and those were the 4 algorithms. Actually, only one of them was suitable to be placed in TLS for key encapsulation, so the Kyber algorithm. The other 3 are signature algorithms. And actually, 3 of them are based on the branch of mathematics called lattice algebra. Now, we talked about the mathematics of RSA, and I wanted to include a very simplified mathematical model for how Kyber and dilithium work, right? I mean, this is difficult to do because it's mathematically much more complicated, but I think it helps to at least develop a mental picture of what is happening sort of there behind the scenes. They are based on the concept called learning with errors, and this is the sort of the core idea there. So you start with a pair of vectors in this lattice space, and what you do is you calculate a dot product between them, and the dot product basically is just a number. And then what you do is you add an error to this number, so you intentionally skew the number. And then you confine it to a predictable range using modulus. This is something that is often used in cryptography. And then finally you get this T, and that's what you publish. You publish one vector and you publish the Q. You keep the other vector and the error secret. And now, as it turns out, it becomes a very difficult problem to find out the missing vector. And the reason why it's so difficult is because of this intentional error that you have introduced. And in reality, it is much more complicated than that, but this is really the essence of the idea with this learning with error algorithms. So in 2024, the first standards were actually created. So Kyber, it lost its cool name and it became known as MLChem, FIPS 203. Dilithium also lost its cool name and it became known as MLDSA, FIPS 204. And Sphinx Plus became known as FIPS 205. Falcon is still undergoing standardization. There are problems there because it's based on floating point numbers, not integers, and floating point operations are notoriously difficult with computers. So it's much easier to do integer mathematics. There's another one that will be standardized this year. It's called HQC, and it's basically an alternative to Kyber. So it was not in the original winner set, but there are many other post-quantum algorithms that were not selected as winners, but that are out there and that could be used. So we are going to return to this topic briefly later. Another thing that NIST did in 2024, at the end of 2024, they published the official deprecation timeline. So they basically said that by the end of this decade, you should stop using RSA 2048 and any algorithm that is of strength 112 bits. And then 2035 was chosen as the sort of deadline for transitioning completely away from RSA and elliptic curve cryptography. Now, this will have to change because of the recent advancements in quantum hardware. So we would expect that this timeline will be accelerated. But for now, this is the official stuff, right? Now, at the end of the day, NIST also, I mean, they have no power to do anything. They are just a standards body, but they are not a regulatory body, right? But many regulatory bodies in many countries, they follow what NIST is doing, certainly in the US, and then many countries then follow what the US is doing. But this timeline has a lot of problems. So the first problem is basically it is too slow, especially for the recent advancements. But even if you consider harvest now, decrypt later, that's probably too slow to say, oh, let's transition in 9 years. Then it doesn't actually differentiate between signatures and key encapsulation mechanisms. And in my mind, and I think most people would agree, the key encapsulation is much more pressing and more difficult and more important because it is about encryption, right? And then signatures are things that generally can be transitioned later. Unless you own a lot of Bitcoin, then you might disagree. Then there's no guidance on hybrid here. So there is a way to actually combine existing cryptography with post-quantum cryptography, but that is not being addressed at all by NIST. And then finally, and I include this, I don't agree with this, but I include this for the sake of the full picture so that you see the different forces and the different lobby groups that are acting on this field, is that for some people, even 2035 is way too fast. So especially, in the sectors that are dealing with embedded like hardware, like automotive sectors, IoT sectors, where often you are planning hardware components, with a lifespan of 20 years or more, then even 2035 is too soon for them. So there's a lot of pushback from those industries to actually push back the date from 2035 to further. Now, the algorithms themselves, that is just one piece of the puzzle. That's like the foundation, right? But then on top of this, you have all kinds of protocols and frameworks and so on. And the most obvious would be TLS. So there is a standardization effort. There are many standardization efforts actually ongoing there. So the one thing that is out there already is this hybrid key exchange for TLS 1.3. It basically combines classical elliptic curve cryptography with post-quantum cryptography with MLChem. It actually does double negotiation, so you get two keys, and then they are mathematically combined into one. So if you are an attacker, you'd have to break both. And this is a very conservative approach. But the reasoning behind it is that, with elliptic curve cryptography, with RSA, we have 50 years of experience. With MLChem, we have like 10 years of experience. So there's danger that maybe we will transition too fast. But of course, ultimately, we would want a pure MLChem TLS, so there is a specification for that as well. And of course, with TLS, you have key exchange, but you need authentication on both sides, so you need a certificate. And of course, there is a specification for that, how to use MLDSA for authentication. And now if you put these two together, then you end up with pure post-quantum cryptography. Now, important thing to consider are the sizes involved, because actually, both MLChem and MLDSA will increase the sizes quite dramatically. So, for example, with MLChem, the amount of data that needs to be transferred between the client and the server would be a kilobyte and a half larger than what we are doing today, which means greater pressure on the involved devices and also on the network. And many embedded devices would not be able to handle this even, right? So it would be prohibitively expensive to have to deal with this, or they might not have enough memory. So there will be like a graveyard of devices that simply, like IoT devices, that simply cannot be updated to post-quantum cryptography. It's even more prominent with MLDSA, where actually the overhead for the signature is like 3 kilobytes compared to RS-256, for example. Now, in terms of what has happened so far, I think the biggest milestone was in April 2025, when OpenSSL 3.5 was released. And it included implementation of MLChem, MLDSA, and SLHDSA, so the three standards that NIST selected. And of course, we know that the world runs on OpenSSL, so that's very good news. And these are the Linux versions that actually now include OpenSSL 3.5. So if you are building, for example, a web service, you have to make sure that you are on Trixie, probably you're on Debian or Alpine, so make sure that you're on Trixie or Alpine 3.22 or higher. Now, it will take time, right? Because we know that not even everybody has moved to OpenSSL 3, right? There are people still on OpenSSL 1.1.1. But at least the pathway is there. Now, because I mentioned .NET in the title, I wanted to include this, which is the Microsoft strategy, which is actually surprisingly conservative, especially in the light of recent developments. Basically, for the past 4 years, not much has happened other than like groundwork. So basically, the algorithms, development of algorithms, so that they can be included into Windows and into different firmwares and so on. And the actual work of integration of those algorithms into the core services like Entra ID and so on, and also, of course, into Windows services and Azure services, that will only come over the next 4 years. So in my mind, this will have to be accelerated, especially in light of recent developments. But nevertheless, in November last year, Microsoft released this GA support for MLChem and MLDSA. SLHDSA is also there, but in experimental state for Windows and Windows Server. Now, this doesn't do anything, it's just there, right? But you can take algorithmic advantage of it if you write code against it. But it's actually not integrated into any of the Windows services stack, for example. So .NET 10 came out at the same time in November, and it included the APIs to actually be able to call MLChem and MLDSA. Again, SLHDSA is also there, but in experimental state. And you need this latest Windows with the latest CNG libraries to be able to actually take advantage of this, or you need to be on Linux with OpenSSL 3.5. Mac is not supported. This will only come in .NET 11. And this is a good moment to very briefly look at the sort of crypto landscape in .NET. So in general, you'd probably interact with the official system API surface, which is system security cryptography. Now, this doesn't provide any implementations. It actually always yields to a native backend, right? So on Windows, there would be CNG, on Linux, OpenSSL, on macOS, it would be CryptoKit, or for older systems, Common Crypto, and so on. And then there's this hardware layer below, like, you know, with hardware acceleration and TPM and what have you. But you don't have to use this, right? What if you would like to use an algorithm that is fully portable? And for that, you can use an external implementation. Like Bouncy Castle is a very popular one because it's implemented entirely in managed code. So this means that you can take it and you can use it without any OS dependency. So you can use it in WASM, for example, inside of a browser. There are others as well. So there's actually quite a few of those. And some of them would have their own native dependencies. But in general, the point of using this sort of non-system algorithms, non-system libraries, is so that you can use algorithms that are not implemented in the operating system. And of course, in post-quantum cryptography, that is very important because there are many algorithms out there. And this actually now leads us to the project called Open Quantum Safe, which is sort of like the center of the universe when it comes to post-quantum cryptography. It's an open source project that is governed by University of Waterloo in Canada. And it provides quantum-resistant crypto algorithms written in C. So you can sort of compile them for any platform if you want. And that's not just the three that have been standardized by NIST, but many more. And they used to have a .NET library as well, but they abandoned it a while back to focus just on the core stuff. So I made a new one some time ago. Now it's not official, so I didn't want to call it libOQS.net, so I called it maybe libOQS.net. But it's really just a thin wrapper, right? And it basically exposes everything that libOQS, so Lib Open Quantum Safe, does to .NET developers. And there are many algorithms there. So for key encapsulation mechanisms, you actually have 9 algorithm families there. So Kyber is still there. It will be removed because it's effectively a duplication of MLChem. But nevertheless, altogether, there would be 8 with like 40 variants, right? And HQC is getting standardized. What will probably get standardized is, I think, FrodoChem or NTRU might get standardized as well. So there will be more things that are getting standardized, right? That's the whole point. So you can use them through libOQS.net. And it's the same with signature algorithms. So there's 7 of them, even though only 2 have been standardized so far. And if you count all the variants, there will be like 200 variants here. And this is basically the full landscape now, right? So if you'd like to do PQC on .NET, then you could use system security cryptography, which gives you access to 2 algorithms. The third one is experimental. You have to be on the latest Windows or on Linux with OpenSSL 3.5. On Mac, it will not work. And you have to be on .NET 10 as well, at least. With Bouncy Castle, it's fully managed implementation. It will be the slowest because of this. But because it's fully managed, you can put it everywhere, right? So you can put it into WASM or into some esoteric, I don't know, like Xamarin out of support for a year and a half, you can still put it there. And there's 11 algorithms last time I checked there. And then with maybe libOQS.net, you basically get access to whatever is in libOQS, which is the most algorithms, and you have generally quite good portability because it works on all desktop platforms for both x64 and ARM64. And it's .NET standard, so you can use it in like, you know, .NET that is lower than .NET 10. And I think that's that. So I wanted to show you some examples now. Is this large enough for somebody who is at the back? That's large enough. It's good for me, but okay. Oops. Okay. So this is an ASP.NET Core application. It's just a very basic application. It doesn't do anything. It just has like a hello world endpoint, except it will just tell us the details of the TLS connection. And it loads a custom certificate because I will load a custom certificate into this application so that we can do HTTPS. Now, I will run it in Docker, and this is the Docker file. And there's nothing special about this Docker file, except it uses Trixie. So it will use Debian with OpenSSL 3.5. And I will self-generate or generate a self-signed certificate using OpenSSL. And you can see that this is a standard ECDSA certificate. So there's nothing post-quantum about this, right? So this is just a standard application. And I have a command here that I saved because there's a lot of typing. So if I now run this in Docker, it now started, and it tells me that the connection is on, which is fine because it's a self-signed certificate. But if I go over here, it works, right? And it says TLS 1.3, AES 256. But if I open the security tab here, you'll see that for TLS, we actually use for the key exchange, we use this hybrid mode. And the reason why this was used is because I was just in a system, like in this case Debian Trixie, that is capable of handling post-quantum cryptography. And this is implemented in all the browsers today. So as long as the server has the capability of doing post-quantum cryptography, this hybrid mode will be used automatically. Even if the certificate that is used for authentication is like ECDSA, so it doesn't have to be MLDSA certificate. So this is the bare minimum that you need to do to get going, so it's super simple. But we have a more interesting case where I have the same application, it's the exact same application, but I set up the Docker file differently. So this is the same application. Now the Docker file is copied, so it starts with using Debian 13. But actually the certificate that I will generate is now different. It is going to be an MLDSA certificate. So this will be now using post-quantum cryptography for authentication. And I'm going to sort of poke around here with OpenSSL, and I'm going to force OpenSSL to not offer this hybrid key exchange, but actually to only offer MLChem 768. And with this in place, I can run this. Here. And now it's running, or it should be running. So I see it here in my Docker desktop. And now I need a client to call this. Now I cannot call this from Windows, because even though Windows now has those post-quantum crypto algorithms in Windows, they are not integrated into anything. So in Windows there is this S-channel stack for doing TLS, but so it's not going, those algorithms are not going to be respected there. So I need a client that is actually capable of understanding this type of handshake. And so of course for that, I need also OpenSSL 3.5. So I'm going to run the client also in Trixie. And this is basically the single command that is needed for that. And I'm going to run it because it will take a while. But in the meantime, we can actually have a look here. We are going to call it twice. Once with OpenSSL S client, to see what is the TLS handshake, and the second time we are going to call it with Carol, right? And so this, I think, has worked. So if I make it larger, I think somewhere here we should be able to see. Yeah, here. So this is the SSL connection, and the SSL connection went over MLChem 768, and the identity of the certificate was MLDSA. So that is pure quantum cryptography. So that is like the peek into the future, basically. Now, the other thing that I have here in the demos, this is maybe not as exciting, is I have a sample console application somewhere, which is .NET 10. So it's going to have access to system security cryptography with MLChem and MLDSA. If you are on the supported system, so here I'm on Windows, so it will work. I'm also referencing libqs.net and Bouncy Castle. And basically, in this application, if I run it, I have like in-memory implementations of MLChem, MLDSA for all three variants, right? So that they can be compared and contrasted. And so for in each case, it's like maybe 20 lines of code to do, MLDSA and to do MLChem. It's a lot of logging here, but doesn't matter. And the point is that I show it to people so that, if you'd like to get a feel of how these API surfaces are and what are the differences between the different libraries, then you can just have a look, because they are really doing the exact same thing. So, for example, I'm going to do ML-Chem with system security cryptography, and notice what happened here. So it started with Alice generating a public and a private key, and then Bob used the public key of Alice to initialize this key encapsulation. This basically gave him the secret and the ciphertext, which went back to Alice, and Alice used that ciphertext to recover the secret, and now they have the same secret. And I can replay this for any implementation, right? So like for bouncy castle, and maybe it was not obvious here, but it is a tiny bit slower with bouncy castle because it's in managed code, right? And with liboqs.net, it would work the exact same way. So that's there, but it's not that exciting, so we'll move on. But if you'd like to look at this later, then I'll have a link. So now this is, I think, a more interesting demo, so I'm going to run this. I need actually two applications here. I have a Blazor application, which will be the client application, and I need, a SignalR server, and this is this. So this is a, it is actually a chat application. You can see that it looks horrific, right? Which is actually a proof that I wrote it, not AI. And it is a chat application. And so the interesting thing about this is that this is pure WASM. So the Blazor here is only on the client side, and we will do cryptography in the browser in WASM. And this is not possible with system security cryptography. It's only possible with bouncy castle. And so we are going to do post-quantum, like end-to-end encryption. So I'm going to join this chat. So my name is Filip, so I'm going to join as Filip. I need a second name. I need like a Norwegian name. I don't know, Tore Andre Flo used to play at Chelsea. And so what has happened now is that Filip joined the chat and Tore has joined the chat. And now they see each other's public keys. And the reason why they see each other's public keys is that if I jump over here, and it's a really bad implementation, it's all in like a Razor file, right? So you have like the diffs here and the UI, and then you have the cryptography. And so what happens is that when you join this chat, effectively what happens in the browser on the client side, an ML-Chem key pair is generated. And the private key is kept in the browser in WebAssembly, and the public key is announced over SignalR to all the participants in the chat. And now there is a button here which can be actually triggered from both sides. And when this button is triggered, this function will run negotiate secret, which will basically perform an ML-Chem key encapsulation mechanism. So whoever triggers this, actually we can trigger this, so Filip will trigger this. So whoever triggers this, if I go back here, we will use the public key of the counterpart. So in this case, Filip triggered this, so he uses the public key of Tore to trigger this encapsulation. And this creates a ciphertext and a shared secret. Now the secret stays in WebAssembly, and the ciphertext is sent over to Tore, right? And then there's this incoming negotiation, which then executes on the other side, where the ciphertext comes in, and what Tore is going to do, he will use his private key to perform the decapsulation, and this gives him the shared secret, which is now identical to what Filip has. And this is this thing that is printed. And at this point, they have a 32-byte shared secret, so they can go and switch to AES 256. Now, again, AES 256 will be difficult in the browser from WASM, but we can still use bouncy castle for this. And so basically now they can do end-to-end encryption, right? So this guy can say hi, it will get encrypted, and it gets decrypted on the other side using the same key, right? So it works both ways. Now, this is not, and by no means, this is not a reference implementation on how you should do an end-to-end encrypted chat. There are protocols for this, like Signal has its protocol that is public and so on. But it is, I think, a sort of a very low-key, very simple demonstration of how these algorithms can be deployed in like more real-world scenarios, other than just thinking about like TLS and so on. Because at the end of the day, there are a lot of practical use cases for asymmetric cryptography as well. So if you'd like to have a look at this, then you can have a look at it later. And the final thing that I wanted to show you is the integration into the identity server. So into token signing. So if you've done any security with .NET, for sure you have used, where is it? This. You have used Duende identity server. which is a very popular identity provider for .NET. And what it does, it uses RS-256 by default to sign tokens. And what we can do is we can actually tell it to use MLDSA. And so this is done here. Now this is not supported out of the box. So this is possible because I made this package called stratweb dilithium duende identity server. And if you pull it in, it will basically allow you to configure MLDSA in identity server. And you can do a number of things. You can use a pre-created credential if you have one, or you can let identity server manage it, which is, I think, what it does anyway by default. So what I'm going to do is I'm going to run this identity server. And now when it's running, I can go over here and open the JSON web keys document from this server. And you can see that it publishes one key, and the algorithm is MLDSA65. So this is what we wanted, right? And then once you have an identity server that can sign tokens with MLDSA, what you need is you need an API, of course, that you can call, that is protected with this identity server, that can also understand MLDSA tokens. And here I have a very simple ASP.NET Core API. It only has a single endpoint with hello world. And it's configured to actually trust this identity server, right? And I have to tell it to be able to, that you will have to deal with MLDSA tokens. And this is not supported out of the box as well. But for that, I made another sort of package, like a sibling package called stratweb dilithium ASP.NET Core. And with this, you have everything that you need. So I'm going to comment it out and run it without it so that you can see that I am not lying. And this now starts the API. And I have now a console client as well that simply fetches the token, and then it actually goes and calls the API. And this console client should give me a 401, and you see here that there is a 401. And if I scroll up somewhere, it will say that, it doesn't understand what it is. Signature validation failed. And the token itself is quite interesting because this is the token that we got. The token is now signed with MLDSA. And if we go over here to Jot.io, this is a typical Jot token, right? So this is the signature that you would normally have with Jot tokens. Now look what happens when I paste this one. The signature is like this, because it's 3.3 kilobytes of signature. But you can see within the decoded token that this is MLDSA65. So I'm going to come back here, and I'm going to restart this application, and now run it again, or run the client again, and now the client has managed to call the server. So basically now we have moved to post-quantum cryptography also for token signing. Now this is not as pressing, I think, as cryptography, as we said. For example, identity server by default rotates the keys every 3 months. But there is still, even in such a setup, there's like a 3-month window that somebody can actually decrypt your key and start self-signing tokens, right? So I guess this is also something that you have to keep in mind. And with this, I think we are almost done. Let me, where are my slides? Somewhere here. I think we are done, yes. So, according to my timer, we are at 59 minutes, 42 seconds, which means there will be no questions. Thank you so much. If you would like to see those slides, they are online. They are just a web page. The demos are also online on my GitHub account. And I think that's it. No, but if you would like to chat about any of those topics, then just grab me afterwards. You can also talk to Claude or to ChatGPT, I guess. but you can also talk to me. So yeah, that's it. Thank you so much.